Hello everyone, welcome to lecture 5. In this lecture, I'll be continuing my discussion on number system, and most importantly, I'll be discussing about number representation. So, what is number representation? Think of when we add two positive number or we add two negative number. We need to tell computer that this number is a positive number or this number is a negative number. How will the computer understand all these things? So there must be a way of representing numbers, both unsigned and signed. Let us see how do we represent these unsigned and signed numbers in a computer. So unsigned binary number. By unsigned binary number, we say that there is there is only unsigned numbers. So there is no possibility of signed numbers. So no negative number is possible. Only unsigned numbers are possible. How do we represent it? For an n-bit binary number, n-bit binary means a 2-bit binary number is represented by 00, 01, 10, and 11. You see, for a 2-bit binary number, we have 4 possible combinations, right? And it is represented by 0, 1, 2, and 3. We can represent numbers from 0 till 3 for n equals to 2. So how many distinct combinations are possible? 2 to the power n distinct combination are possible. 0, 1, 2, 3. N equals to 2, 2 to the power 2, that is 4. 0, 0, 0, 1, 0, 2, and 0, 3. And what is the range? Starting from 0 to 2 to the power n minus 1, basically. So 0 starting from 2 to the power n, which is 2 to the power 2 minus 1, that is 3. So we can only represent number from 0 to 3. So a binary number is represented by B0, B1, B2 up till Bn minus 1. So let us see for n equals to 3. N equals to 3, there will be 2 to the power 3, 8 distinct combinations, and those 8 distinct combinations are starting from 0 till 2 to the power n minus 1. What is 2 to the power n here? 2 to the power 3 is 8, minus 1 is 7. 2 to the power 3 is 8 minus 1, which is 7. So we can represent numbers starting from 0 until 7. Similarly, for any other range, n equals to 8, n equals to 16. So this is the largest number that I can represent using unsigned binary numbers. If it is not clear to you, please understand it. I want to represent unsigned numbers. So let us say that we do not have any signed numbers in our consideration, and we need to represent unsigned numbers. If n equals to 8 or n equals to anything, the highest number that I can represent is 2 to the power n minus 1. And it starts from 0. As it starts from 0, so we can represent a number 2 to the power 0 till 2 to the power n minus 1. So for n equals to 8, 16, or 32, this is how we represent. So the largest number that we can represent for n equals to 16-bit is 65535. We'll see a lot of example when we perform, this when we start writing codes in C, how many numbers we can represent under a particular data type, integer, unsigned integer, signed integer, etc., etc. We'll look into all these things in details. So these are very much essential, and your understanding here is required. So please try to understand it nicely. Now let's see. Of course, we will need both signed and unsigned representation, right? So for signed integer representation, there are many numerical data items that are used in a program which are signed numbers, right? So we need both positive and negative number. Only positive number will not help, only negative number will not help, but we need both positive and negative number. So now comes the question, how do we represent it? There are various ways of representation. One possible way of representation is sign magnitude representation, which was used earlier. One's complement representation, which is easier to represent. But two's complement representation is the one which is widely used and which is adopted by everybody. So out of all these three approach, we'll look into all the three approach in detail in the in class, but I'll briefly discuss about each one of them. And two's complementation basically is something which is used in today's computer. Okay. So for sign magnitude representation, for an n-bit number representation, the most significant bit indicates the sign. Okay. So if you have n-bit representation, so one bit is fixed for sign. Okay. 0 means it is positive, 1 means it is negative. The remaining n minus 1 bit represent magnitude. So b equals to 0, 1 up till bn minus 1 is basically the magnitude, and bn minus 1 is the sign of that particular number. How do we represent it? So 0 means positive, 1 means negative. So if you see 0, 0, 0, 0, 0, it's a positive 0. Then 0, 0, 0, 0, 1 is positive 1, and so on. 0, 1, 1, 1 is positive 7. If you represent the next one, you see this is 1, 0, 0, 0. So this is basically minus 0. Although we do not need minus 0, but still it is there because of the representation, the way one's sign magnitude works. Okay. Similarly, 1, 0, 0, 1 is minus 1, and so on and so forth. And 1, 1, 1, 1 is minus 7. So 15 distinct numbers are represented in 4-bit, right? In unsigned number, we can represent 16 distinct numbers, but for sign, 1 bit is basically your 1 bit is basically sign bit. So that is how we can represent 15 distinct numbers. Let's see one's complement represented. One's complement is very straightforward. What is the basic idea? Let us see. Positive numbers are represented exactly in sign magnitude. So for positive number, we need not have to worry. If it is a positive number 1, then it is just 0001. Okay. For a 4-bit representation, 0001. For negative number, if you have to represent minus 1, then what we do? We have 0001, which is a positive one. We add 1 to it. Okay. So the negative numbers are only represented in ones complement form. So for doing this, what is basically done to get the ones complement, we complement every bit of the number. 1 is converted to 0 and 0 is converted to 1. So what is the representation of 1 in 4-bit? 0001. So one's complement representation will be 1110. Okay. So 0 is converted to 1, 1 is converted to 0. And most significant bit will indicate the sign of the number. So it becomes minus 1. This is how it works. Okay. Let us see this example. So 0 to 7, 0 to positive 7, there is no change. This is exactly similar to your sign magnitude representation. But you see the difference here, uh, starting from then how do we represent the negative number? So what is minus 7? What is plus 7? Plus 7 is 0, 1, 1, 1, right? If you complement each one of these numbers 0, 1, 1, 1, what it will come? 1, 0, 0, 0, which becomes minus 7 basically. Now you see 6. What is 6 here? 6 is basically 0, 1, 1, 0. So what will be minus 6? We just have to complement it. So here 0 becomes 1, 1 becomes 0, 1 becomes 0, and 0 becomes 1. This is how 1001 is minus 6, and so on and so forth. But here also, see, we have plus 0 and minus 0. So this is an example I'll be discussing in the class maybe. But you see, both sign magnitude and in one's complement, there is two representation of 0, minus 0 and plus 0, but there we just 0 is 0, right? We need not have to have negative 0 basically. So how, but both one's complement representation and your sign magnitude representation does not take care of this. So 0 is not represented just once. 0 and minus 0 is represented. 0 is represented at minus 0 as well. Uh, let's see what happens in 2's complement now. So this is a problem, right? Because we do not need minus 0, but this is taking an extra space, using which we can represent another extra number, right? So let's see what is 2's complement representation. So what is the basic idea? Positive numbers are represented exactly in the sign magnitude form. So the way we were representing it using in one's complement, the positive numbers are are also represented in two's complement as in sign magnitude form. Okay, there is no difference here for the positive number. But for the negative numbers, these are represented in terms of two's complement form. It's not one's complement, it's two's complement form. So how to compute the two's complement of a number then? For computing two's complement of a number, all we need to do is that we complement every bit of the number. So complementing every bit, we already know how do we do it. We convert 1 to 0 and 0 to 1. But then there is an extra step. We need to add 1. So 2's complement, this is an overhead where we need to add 1. Okay. In sign magnitude and in 1's complement, we did not have to do any addition or anything to get the numbers in to represent a negative number. But to represent a negative number, here if you see that we need an extra addition. So first we have to convert the number to 1's complement, then we add 1 to it. MSB will indicate the sign of the number. If it is 0, then it is positive. If it is 1, it is negative. You need to remember these steps. How do we represent a number in 2's complement form? This is how. And how do we understand that this is what number? Okay. So 0 represent positive, 1 represent negative. So this is how it goes. 0, 0, 0, 0, 0, 0, 0, 1, and up till 7 there is no change. But let's see what happens uh, from minus 8. How do we represent minus 8? How do we represent 8 basically? Uh, we represent 8 as 1, 0, 0, 0, right? And if we convert that to 1's complement, it becomes 0, 1, 1, 1, right? And then we add 1 to it. What will happen? 1, 1, 0, carry 1, 1, 1, 0, carry 1, 1, 1, 0, carry 1, and 1 and 0, 1. So it comes to 1, 0, 0, 0, which is minus 8. Similarly, if you convert any of these to 1's complement first and then add 1 to it, you will get the 2's complement of these numbers. Okay, let us see how do we represent minus 4. So what is plus 4 first? We know plus 4 is 0, 1, 0, 0. Okay, and then we need to know the 2's complement of 0, 1, 0, 0. So 2's complement of 0, 1, 0, 0 is 1, 0, 1, 1 plus 1, right? Which is 1, 1, 0, 0, which is minus 4. Okay, so this is how. First we need to do 1's complement, then we add 1 to it, and then we get the 2's complement of the number. Okay, this is how it works. The beauty of 2's complement here is that you see there is no minus 0. 0, 1, 2, 3, 4, 5, 6, 7, minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1. So we can represent 16 distinct numbers here using 2's complement. Why? Because there is no representation of minus 0 here. Okay, but at the expense of one extra addition that we have to perform. Okay, everything comes with a cost basically. This is how we perform 2's complement. Now, so now we have understood that how we can represent numbers, how we can represent signed numbers, how we can represent unsigned numbers, and so on. Let's move on. What is a typical number representation in C? For shortened, it is 2 to the power 15 minus 1 to the power minus 2 to the power 15. So we'll see these things in detail in the in class basically. So firstly, for any n-bit number, what is the range? You need to know the range. The range I'll be discussing in detail in the in class lecture. Okay. For a 32-bit, it is this, and for a 62-bit, it is this. Okay. Basically, it is 2 to the power n minus 1 minus 1 to 2 to the power n minus 1. Okay. This is how it goes. Next comes is representation of characters and strings. Okay, how do we represent characters and string? Because we also need characters and string in a program, right? And we also need to represent that in a computer. How do we do that? So all these things, how do we represent characters, what is ASCII code, etc., etc., we'll be discussing in detail in the in-class lecture. I hope this lecture is helpful for you, and you should brush up a little more such that we can solve problems in the class itself. Okay, so thank you very much for your attention.